My name is Liran Haimovitch, and I'm a co-founder and CTO at Rookout. Before founding Rookout, I spent about a decade doing cybersecurity stuff, where much of our focus is understanding how software actually works, understanding what's going on behind the scenes, and making it do whatever we want it to do. So that came in very useful as we started out Rookout. Rookout is a data collection and debugging platform. We allow our customers to connect to their application as they're running anywhere in the world and collect any piece of data they want without writing any more code, restarting their application, or redeploying it just by clicking on the line they want. And developing Rookout, there's been many challenges. Some of them have to do with security, some of them have to do with UX, some of them have to do with how do we actually make the magic work. How do we create a debugger that can be used in production and collect any piece of data? And today I want to share with you some of what I've learned, some of the knowledge we've come across as we were developing the Python SDK for Rookout. So what's your favorite debugger out there? Or are you just using printf? So the Python standard library has PDB, which is the Python debugger, a built-in basic debugger right there. You also have the PyDev debugger. It's open source on GitHub, and both the Eclipse environment for Python and PyCharm use it. Rookout supports debugging Python in addition to JVM and Node, and some other IDEs such as Python Idle and Atom have their own built-in Python debuggers. What most of those debuggers have in common is this scary function. It's called syssetrace. It's probably the most complicated function I've come across in the Python standard library. That's the documentation for it, which has improved a bit over the last few years, but it's still quite daunting and not very easy to understand. So I'm just going to walk you through it step by step and make sure we all understand what's going on here in 30 minutes or so. So what does syssetrace do? Syssetrace registers a callback for the interpreter, and whenever the interpreter wants to notify us, the debugger, that something important is about to occur, it calls our callback. There are 4 basic events: function call, line execution, function return, and exception raised. Whenever the interpreter is about to execute one of those events, it's going to call our callback just before it does. This is what the callback can look like. The function is called simpleTracer. It receives 3 arguments. That's the syssetrace interface. If frame is the first argument, it's the state of the interpreter just before our callback is executed. Event is an indicator which of the 4 events we are going to be receiving. It's a string. It's either going to be call, line, return, or exception. And arg is an optional argument that may provide additional context on the event that's about to occur. This function starts by extracting some information about the event that's going to take place. We extract the function name and line number, and then we print the event, function name, and line number to the standard output. Finally, the function returns itself, and we're just going to discuss it in a bit. Let's see what happens when we run a sample code with our sample tracer. Function A returns b times 2. Function B returns a string. We call syssetrace, and then we call A. So calling syssetrace doesn't have any output. Neither does calling A. But just as we enter A, our callback is executed for the first time. We get the argument call, the function name is A, and the line number is 1. The second event is a line event. Function A, line number is 2. Then we get a call event. Function name is B, line number is 4. And line event. Function B, line 5. And now we're going to see unwinding. Return from function B, line 5. Return from function A, line 2. That's a very brief introduction to syssetrace. As I've mentioned, simpleTracer returns itself. you would see most callbacks for syssetrace return themselves in some or all cases. And the reason for that is because there are actually multiple callbacks behind the scene. When you call syssetrace, you register a global trace. The global trace is thread specific, and it's going to be invoked whenever the interpreter creates a new frame. Whenever the interpreter goes into a function, it creates a new frame, and it's going to invoke us with the call event. What we return from that callback will be the local trace. And the local trace will be set as part of the frame. Now, whenever the line return an exception event occur within the frame, the local tracer will be the one to process it. Keep in mind that determining whether or not we have a local trace will always happen using the global tracer, regardless of whether we have a local tracer or not in the frame. And that once a frame is started, there is no documented way in Python to set the tracer for it. So we either set it before the function is invoked, or we don't have any option setting it in retrospective. Let's take a look at how it looks. When we call syssetrace, we set the global tracer, simple tracer. When the call event for A is executed, we return simple tracer, which is set as the tracer for the frame. And when B is executed, we return simple tracer, which is set as tracer for the frame. As we return, the interpreter is unwinding the stack, and it's going to use the local tracer of the relevant level. Now, as I've mentioned, syssetrace sets the global tracer per thread. There is no documented way in Python to set the trace function for a different thread, but the easiest way to go about it is by using the threading setTrace function. This function, which also accepts a callback, will actually call syssetrace with our callback for any new thread created by the threading module. So we call threading setTrace, and threading setTrace will call syssetrace for us. Keep in mind that you want to call threading setTrace as early as possible, because there are no documented way of setting the tracer for a remote thread. And also keep in mind that other low-level implementations for threading, such as the thread module, do not offer that option. Last but not least, if you are debugging an event loop-oriented application using gEvent, EventLet, or GreenLet, then from Python's perspective, there is only a single thread. So the global tracer function is going to be shared among all the greenlets. Now, if what I've shown you here seems a bit daunting or confusing, then you might be wondering how easy it can be to build a debugger for Python. Lucky for us, we have a shortcut. The PDB is actually built on top of BDB. BDB is base debugger, and it's part of the Python standard library, and we can just inherit it and build our own simple debugger. We start by inheriting from BDB, and you creating our constructor. We call the BDB inherited constructor. We create a breakpoints dictionary to keep track of our breakpoints, and we call setTrace, which has BDB install its own tracer function using syssetrace. Now, the next step is adding our setBreakpoint method, which accepts a file name, a line number, and a method, and calls setBreak from BDB to do the magic and just install our breakpoint within the dispatcher, within the trace function. And then all we have to do is record the breakpoint, file name, line number within our breakpoints dictionary, and keep track of the methods we want to call. Finally, we inherit userLine, override it. UserLine is called by BDB whenever it wants to inform us that a userLine is about to be executed. It can happen for breakpoints, but it also happens for other events BDB cares about. We don't, so we start by making sure it's a breakpoint, and if not, we return. Then we get the file name and line number from the frame. We get the list of breakpoints we want to execute, and we execute them. That's pretty straightforward way of building a Python debugger. But performance, that's a big issue. I mean, if we are aiming to have our debugger working production scenarios, then we care a lot about what's going to be the performance impact of it. So at Rookout, we went ahead and tested that naive implementation. We created two test methods, empty method, which is just pass, and simple method, which has 10 assignment statements. And we ran each of those functions 16 million times in a loop in 4 scenarios without a debugger as a benchmark for how fast Python is, with a debugger but without setting any breakpoints, with a breakpoint in different file, and with a breakpoint in the same file. So here are the results for the initial run. Without a debugger, Python does 88 milliseconds in average for 0.088 milliseconds for the empty method and 0.1799 for the simple method. As you can see, overhead is ginormous. We're talking about 100x, maybe more. So that's obviously not performance grade performance. So how do we optimize the debugger? First of all, as you remember, we have both the global trace function as the local trace function. As I'm sure you can imagine, the local trace function is invoked a lot more than the global trace. And by avoiding local tracing as much as possible, we make it a lot faster. So the first thing is be as smart as possible about whether or not we need to trace a specific frame. The second thing is make that decision. Make the call decision about whether or not we want to trace a frame as fast as possible. And last but not least, optimize the line events. When we are local tracing, line events are the most common, so make it as fast as possible. We went ahead and deleted a whole bunch of, we forked BDB, deleted a whole bunch of unused features, optimized for hot path, and this is what you've got. It's obviously a lot better, but still not quite there. How many of you are familiar with Cython? Awesome. Well, Cython is a compiler for Python code. It takes your Python code and generates C code that's using the CPython API. So essentially, you are recompiling your Python code into C code, which is much faster, but it's completely compatible. You can directly call that new object as if it was a Python module, because it implements the same interface. So we went ahead and compiled our BDB using Cython and got a pretty nice improvement. But around here we will start questioning ourselves. I mean, is this going to be fast enough ever for production? We stopped for a second and tried to collect some insights. Python BDB is really quite naive. It was never meant for production use, and there's a lot to be optimized over there. But obviously, the more you optimize it, the harder it is to continue growing, the harder it is to make it ever faster. And we wanted to see how fast can we theoretically make it. What happens if we install an empty tracer that does nothing but return? What's going to be the overhead for that? And that simple test gave us this result. That's 4 times to 10 times slower once you activate local tracing. And at this point, we started figuring out tracing might not be the way to go. We might never be able to make tracing fast enough for production use. We dove into CPython, trying to figure out why. And it seems that once you turn on tracing, you are setting up CPython for a lot of extra work. Some of it happens in Python, in our tracer. So for every instruction the user is doing, we have to do a few instructions to evaluate, trace all those events. But some of that extra work actually happens in C. For instance, maybe call line trace is invoked after every instruction, trying to figure out if we're going through a line boundary or not, and deciding whether or not to trace it. And it seems that CPython is far from optimized here, and there's probably a lot of work that can be done. But as we are trying to support existing customers without having them fork their Python interpreter and go through complicated installation procedures, that's obviously not going to work. So what did we do? How did we go about creating an SDK that allows you to debug in production with no overhead? Well, let me take a step back and discuss a bit bytecode. How many of you are familiar with the concept of bytecode? It's most of you. Well, the Wikipedia definition of bytecode is a form of instruction set designed for efficient execution by a software interpreter. It's a pretty big word, but essentially Python compiles our source code into a bytecode. This is what it looks like. We have a simple function here. Multiply AB, assign to result A times B, return result. Do any of you have a guess what's the bytecode for this function looks like? That's the result. Python takes our text, goes through lexical parsing and other processes and just creates a buffer. In Python 2, most buffers are obviously strings. And that's what the interpreter is executing as our application is executed. That's unreadable for most of us, but if we go through the Python this module, we can get something that's a bit more human readable. It's a classic stack-based virtual machine. Load A, load B, binary multiply them, store the result into result, load result onto the stack, and return it. Those are the logical instructions the interpreter is executing as it's going through that string. The stages of the interpreter are the following. It starts by compiling our source code and generating the bytecode. The bytecode is often cached in those PYC files, I'm sure all of you are familiar with, and it's also in memory. Then the interpreter goes into the execution loop. It loops through the strings, loops through the buffers, executing each instruction on its turn. And this is where tracing happens. Once we turn on tracing, the interpreter constantly asks himself, is this something the tracer cares about? Is this a function call? Is this a return event? Is this a line event? And if so, it calls us. So that by turning on tracing, we actually make the interpreter loop slower. As you can see, quite a lot slower. Trying to approach this problem, we took a different route. We went back to the bytecode. A Rookout goes into the bytecode in memory, finds the this line of code where it is. So if you are, say, going to line 5, we are going to find the start of line 5 within the buffer, and we are going to add a call instruction to Rookout. And such, the interpreter doesn't care about us. The interpreter loops through the code. It doesn't know that Rookout is even there. Once it sees the regular call instruction, it calls Rookout. And that's how our breakpoint happens, is invoked. Now, bytecode manipulation is quite a big topic, and I'm not going to dive into that a lot more. I do want to share with you some useful tools if you care to learn more about the topic. So the Python standard library has a couple of useful utilities. The first is the inspect built-in module, which allows you to look into the interpreter state. And I'm going to share a bit more about that. It lets you see the code for any function or class anywhere. And you also have the this module. The this module allows you to take those strings, those bytecodes, and reparse them into something that's a bit more human readable, like I've shown you. Now, unfortunately, Python does not offer any way to update the bytecode in memory. You actually have to recompile the code from source every time. And that's a bit of a problem for us. If you are interested in learning more about how you can update the bytecode using the CPython, there is a native extension by Google called Cloud Debug Python that does a bit of that. And that's a great tool to look at if you're interested in learning more and experimenting with it. Now, just for the last topic, I want to share with you some extra info about what do you do after you break. So far, we've been discussing a lot about how do you know where to break, how do you find the line, how do you make the interpreter call you. But once you break, you need to take a look at the interpreter state, at the application state, and collect the data you care about. How do you go about that? Well, I'm sure you remember the first argument for the trace function is frame. Frame is literally the state of the interpreter as it's executing our code. By looking into the frame, we can get any piece of data we want. Local variables, stack traces, the source code, whatever. And the inspect module is well documented and easy to use and allows us to walk through those objects in a very easy manner. Now, unlike what I've shown you earlier, performance here is quite awesome simply because it's very similar to how the interpreter works behind the scenes. It's the same objects and the same method the interpreter used to work, so everything is quite fast and simple. So let's take a look at a few examples. Our function is test frame info. We get the frame by using inspect coin frame. Now, inspect coin frame is quite a useful method, possibly the most useful in inspect. It has some production uses when you're trying to get information about your environment, but it's also amazing for testing and experimenting because it allows you to get the frame of your existing function. So if you're trying to see what the frame is going to look in a certain scenario, all you have to do is build a method that replicates this scenario. For instance, I want a function with test frame info. Just create it, call frame, inspect coin frame, and you're getting the coin frame. And you can use it for whatever you want. And now we print the get frame info of the frame. What you're going to get is a simple traceback object, quite similar to what you see as you're walking through trace if you're familiar with the exception mechanism of Python. We get the file name, frame inspect.py, we get the line number where the frame is currently, we get the function name, we get the code context, and we get the index. The index is our position in the stack trace. So as we are now at the top of the stack, index is going to be 0, and as if you're going to walk up the stack, index is going to increase. Additionally, we have test vars. Test vars allow us to see how local variables look from the frame perspective. We have mystr, which is a string, myDict, which is a dictionary, mylist, a list, and then we'll go ahead and print flocals of the coin frame. Flocals is an attribute of the frame which allows us to access its local variables. Local variables are literally stored as a dictionary. Variable names are keys, and variable values are the values within the dictionary. So that myDict is a dictionary, mystr is a string, mylist is a list, all of it within a dictionary. Fairly straightforward, much easier to use than what I've shown you earlier. So what can you do with all I've shown you today? It might not be as practical as a PyTest, but you can use it to show off your Python skills, show how awesome you are and how well do you know how Python works behind the scenes. But there are some legitimate and useful uses for it. For example, have you ever wondered how does the logging module print the file name and line number where you're calling it from? So the logging module calls inspect coin frame, and then it walks up the stack until it finds the first caller outside the logging module. It gets the file name, line number, and function name for that frame and adds it to the log record. You can always also walk up the stack for other reasons. If you are interested in profiling your code or getting that extra bit of context somebody forgot to pass to your function. And obviously, you can go ahead and build your own debugger. That's quite useful. The resources from this talk, including the source code, are available here, and the slides will be online later. Thank you.